again. Okay, so yeah, thanks everyone joining. Thanks to Sam for coming to speak to us. Sam is an assistant professor at the University of Minnesota, and as we just heard from Sam, he's going to be traveling around quite a bit in the UK next year, associated with various places. His work has covered a broad range of areas, including philosophy of science generally, determinism in classical mechanics, space-time theory and gravitation, foundations of quantum physics, philosophy of statistics, and philosophy of computing. Specifically on the topic of idealization, which Sam is going to talk to us about today, Sam introduced the idea of a minimal approximation in one of his papers on Norton's dome, and has co-edited a special issue of Synthase on infinite idealizations in science. So that's a really good place to start if you're interested in all of this. I'll hand over to Sam now for the talk.
Great. Thank you very much, David. So as you'll see from the slides here, what I'd like to talk about is a certain kind of connection between emergence, explanation, and idealization, with special reference to this question that has sometimes come up in discussions, especially in philosophy of physics, but a little bit more generally in the philosophy of science, regarding whether or not there's anything special, unique, or extraordinary about idealizations that involve infinities. The idea of idealization as a kind of distortion plays an increasingly prominent and important role in the development of physics after Galileo. As we're aware, Galileo's modeling of the pendulum as a simple, what we would call a simple harmonic oscillator, and his development of the law of free fall, using not cannonballs probably dropped off of the Leaning Tower of Pisa, but probably rolled down carefully designed ramps such as this, involved him doing things like neglecting friction, long transitions that have to do, in the case of the simple harmonic oscillator, with large amplitude swings for the pendulum. Now, this sort of methodology was picked up and used extensively by Newton himself, and has played an important role in physical theorizing since then. Galileo is, of course, not the first person to use these sorts of ideas, but it's probably where those sorts of ideas within the genealogy of modern physical science find their strongest and most influential expression. There's a lot of modern examples of this. So one that's dear to me is a certain type of idealization that we find in cosmology. Now, in the history of the universe, we find variegated things, and in every sort of configuration at many different scales. The physical universe is rich in detail. Our cosmological models idealize almost all of that detail away. We describe space-time in these models, the FLRW models, as being homogeneous. So space in every direction contains the same things, and isotropic. Space looks the same in every direction. Now, fortunately for us, when we look around ourselves, we don't see things are the same in every direction, and things are not the same in every place. Besides being boring, it would also preclude our very own existence. So these FLRW spacetimes idealize away much of the things that we care about, but nonetheless, when we perform these idealizations and describe spacetime in such a crude way, we can nonetheless make a lot of progress on the theoretical questions we're interested in, trying to understand in some large scale and answer certain sorts of questions, provide certain sorts of explanations about how the universe evolved. Another sort of idealization that has received a lot of attention recently It regards idealizations in condensed matter physics and statistical mechanics. In these sorts of idealizations, although there's a few different types, typically one idealizes any finite system, such as the water that I boiled in order to make this tea here, as not a finite collection of, say, water molecules, but an infinite collection. And in doing so, it allows us, and I'll go into a little bit more detail about why that's so, involving the free energy function later on in the talk. It allows us to describe the boundaries between different phases in terms of a clean, precise line in diagrams like this. We can identify a single state that is on a coexistence state between, say, liquids and gas, or as was the case for the water going into boiling my tea. Now, in order to do this, right, the idealization involves describing a finite system as being an infinite system. There's another example. So this is a non-physics example from population biology. This involves probability distributions for various genotype relative frequencies in the next generation of organisms with respect to a current generation. And these are supposed to represent the different probability distributions for this genotype frequency transmission for generations, current generations of a certain size. And in this simple model, mutation is neglected. And so the probability distribution for a genotype to be transmitted in this population is just based on statistical properties about how genotypes can mix when they transmit to a new generation. There's going to be more variability when there is a smaller population. And so this feature, which is sometimes in biology called drift, allows for the changing proportion of a genotype in a species over time, merely due to statistical fluctuations that are magnified when the population sizes are smaller. So population biologists can describe the mere effect of direct genotype transmission, regardless, setting aside this drift when they idealize the population as being infinite. As the population gets larger and larger, the variance of this distribution gets smaller and smaller, and it approaches in probability a distribution that has all of its support on a single frequency. Okay, so these are some examples of the sorts of things that I have in mind, where we misrepresent the thing that we're interested in. In this case, for instance, no real population of interest has an infinite size towards some purpose. So there's a few questions that arise. So that's a kind of like, I've just observed some phenomena that we see in the context of science. So a general, not very precise question, but one that will nonetheless guide me or has guided me in this work is, what are we doing? Like, what's the deal? Maybe another way of putting it, or putting the underlying unease involved with using idealized models, is how can something so wrong be so right? How can a model which sometimes omits or distorts so severely or so many properties of a system of interest nonetheless be so right for a certain scientific purpose? I think many of you may already have inklings of how to answer this question, but this is the sort of guiding question. And finally, are idealizations using infinities substantively different from those that don't? There's been some hints in the literature of folks talking about phase transitions or optics or some features of quantum theory that invoke the idea that certain types of infinite idealizations are different. More recently, Strevens has argued explicitly that certain types of infinite idealizations are different from other types of idealizations. To answer these questions, I'm going to investigate two sorts of things. So first, I want to get a little bit more precise about what I take an idealization to be. And for that, I'm going to describe what I take the form of idealization to be, idealization's function, and the justification of idealization. Then I'll make a brief comparison between idealization and approximation before I go on to try to answer the questions that I started with. That is to say, what are we doing when we're employing idealized models? Is to suggest that one of the reasons why we employ idealized models is that it facilitates certain types of explanations or certain types of other scientific activities. And they do so because of the idealized models having emergent properties with respect to the models from which they idealize. And so in this section, I'm going to explain what I mean by that, explain the details of that answer. So let's get started. Oh, of course, I wanted to note a point of scope. So I take this project to be a kind of gently normative project rather than a descriptive project. Folks use the word idealization in many ways, and I don't take the work that I'm undergoing here to be any sort of taxonomy or description of the way that the very many ways that scientists and philosophers of science use the word idealization. Indeed, I think those ways are so variegated that there's probably no consistent way of categorizing them. But rather, my goal is a kind of an explication, maybe in the Carnappian sense. My goal, in other words, is to order how imperfect models explain and perform other sorts of scientific roles. So I take it to be a kind of guide for how maybe we ought to think about idealization. Okay, so let's get started then with this first part of the project, talking about the form, function, and justification of idealization. Okay, so here's it in a nutshell. An idealization is a model of some phenomena within a certain class of models that is less representationally accurate than another in that class. So as I'm construing it here, idealization is a four-place relation. One of the places of the relations is the phenomena to be modeled. So if you'll permit me to do a little bit of doodling here to describe how this is supposed to work, I'm imagining that there is some space of phenomena, some collection of phenomena that we intend to model. And there's also going to be relations of similarity between instances of that phenomena. So for example, if you imagine phenomena consist of values of fields, of some physical field, oftentimes those values of fields will take on real numbers as their values. And the similarity between values of fields is inherited by the similarity of the real numbers that describes them. Generally speaking, my attitude is that how phenomena are similar to one another is going to be largely determined by the measurement theory for those phenomena. Measurement theory helps us describe how different instances of phenomena are relatively similar to one another. If we want to formalize this, ends up inducing a structure on the phenomena that has of a topological or uniform structure nature that allows us to describe, for example, how a range of phenomena can continuously or uniformly vary. The third place in idealization is a class of models representing those phenomena. So what I have in mind here is another set. Here we have models. And not only do we have this set, but we have a representation relation. The relation is probably a function. It may be a partial function. But it tells us which models represent which phenomena. And then finally, the fourth element is a particular model in that class. So a particular model in this class might be, say, this one here. Now, that particular model in that particular class will then, via the representation relation, right, represent some particular phenomena or maybe some particular class of phenomena. Now, in the way that it does this, it may do so imperfectly, right? It may be that according to how we are describing models as representing, this model that we've picked out doesn't match with an intended class of phenomena that it's intended to model. And so that difference, right, is sometimes, but not always, an indication that the model is idealized. According to my account here, in order for this model to be idealized, there has to be another in the class of models that would represent the phenomena better. So idealization on this account is intrinsically relational to some class of models that one is considering. I should say also that the representation relations, right, induce similarity relations on the models via their connection to the phenomena. So if the phenomena are similar in different ways, then the models can also be regarded as similar in various ways, similar in virtue of the ways that they represent phenomena. So models might be similar in some respect to the degree that they represent a certain aspect of the phenomena in a certain respect. I want to point to a few features that are
Sam,
important.
do you mind if we interrupt, or would you rather we wait till the end?
Well, I don't know what your standard procedure is.
It's speaker's preference.
Speaker's preference. Well, I think with such a small group, I'd be happy to have a discussion along the way.
So I was just going to ask whether you think it might be context where we need the similarities that we talk about to the models to not be the ones induced by the representation map and the phenomenal similarities. Do we need that extra flexibility to talk about different similarities that aren't just kind of pushed forward or induced?
You certainly can. I think that the way in which the reason why I'm talking about this particular notion of induced similarity on the models is that it's going to play a role in my story later on. That doesn't preclude one considering other ways in which the models could be similar to one another, though.
Thanks.
Does that answer the question?
Yeah, thanks.
Okay, great.
Yeah, the key thing is it's not necessary that that way, but for the story you want to tell, that will be part of it. So,
yes. Sometimes in philosophy, like when we say, here's a thing that we can do, it's implicit that some statement that one should only do that thing and no other thing. And I don't mean to imply that at all. The story that I'm telling is compatible with other sorts of structures that one might imagine on the class of models. Indeed.
But surely the point is, I mean, so far as they're similar qua models, it's got to be because of the representation relation. I mean, if you have two statues, they're not similar in virtue of both being made of marble qua statues, right? Because they're only similar qua statues if they're statues of something similar or in a similar genre of sculpture or whatever, right?
Yeah.
So I would say that Sam's notion of similarity is going to be the more salient one anyway.
This would lead us into a very long discussion of analog models and isomorphism that I think it would be best to avoid. But I think let's save that for a conversation in the real pub when we can have one.
Yeah, that sounds wonderful. I think James' comment is representative of kind of like why I'm thinking about the similarity relations on the models as being induced by the representation relation. That's going to play a little bit of a role later on when we talk about the justification of idealization. So I wanted to point out one feature of this account of idealization is that it does not require that there is a perfect model. It doesn't require that there is a model in the class that completely accurately represents all aspects of the phenomenon. Another feature that I want to highlight is that this account allows for representational accuracy to be multifaceted. So maybe I can describe that in a little bit more detail here. So maybe I should start with a little bit more on the collections of models. So in physics, oftentimes we can give a precise account of what models we're using. Lorentzian manifolds, vectors in Hilbert space, like states on C-star algebras or something like that. But in most of science, it's not so. The collection of models is often only tacitly given, vague, and elastic. What that means is that corresponding questions about whether a model is idealized or not will also have a certain amount of vagueness to them. I don't think that's necessarily a problem, but it's something that needs to be realized when we're coming to try to understand a particular case in scientific practice, whether it's idealized. Furthermore, whether a model is idealized depends on our understanding of the phenomena. So for instance, when models fail to represent phenomena without evidence of idealization, that can be an impetus to a new discovery. So in this standard story, right, one idealizes, for example, the description of the motion of a planet like Uranus in the night sky, accounting for all the known astronomical bodies. And one shows that even when one starts to relax idealizations and calculates with more and more precision how those different bodies affect the orbit of Uranus, one finds that it doesn't quite match up. And this was an impetus for the postulation of a new planet, Neptune, by Leverrier, which was subsequently discovered. And similar story can be talked about regarding Mercury and its relation to the general theory of relativity, although of course the historical details are complicated, involving a phantom planet called Vulcan. The significant point though is that sometimes as our understanding of the phenomena improves, we can gain better understanding of whether or not a model is idealized or not. Because whether a model is idealized is relational to the phenomena that it intends to represent. So for every aspect of phenomena, there's going to be some way to idealize. And so accuracy in general is only going to be a kind of a partial order. So idealization's distortion is a local phenomena on my account rather than a global account, rather than being global. It's away from a better model, not the truth. So this is in reference to the description that I mentioned, where I don't require for my account of idealization that there is a perfect model within the class of models that one is interested in. So let me give you an example. This is really a toy example, a kind of cute example, but I think it's worthwhile. So we can imagine a simple model of a helicopter. This is not a good helicopter. Try again with this helicopter. Here we go. Doop. So a helicopter, right, produces lift by the spinning of its main axis. And it also has this dorsal blade that also spins in a direction. And there's a few things that we might be interested in. We might be interested in calculating the lift that a particular helicopter undergoes. But we might also be interested in describing not also the lift, but whether or not the helicopter, for instance, rotates in a particular direction. So we can imagine, for instance, a multi-dimensional space of different features whereby we're representing the helicopter. One dimension might be lift, another dimension might be rotation, and a third dimension might be the inclusion of the components, the mechanical components of the helicopter. So one type of model of the helicopter calculates the lift by suitable equations via the rotation of the main helicopter blades. So here we get an accurate, a more or less accurate description of the lift and an accurate description of the rotation, but not necessarily a good description of the components. The reason why is that it doesn't include, for example, the rotational, the torque that the rotating blades induce on the main body of the helicopter. So even though so we might place that particular model at this particular point in this space. It gets the rotation pretty good, the lift pretty good, but when we project down to the component axis, it doesn't describe certain mechanical components of the helicopter. Now, one thing that we might do is we might therefore include the effects of the torque, so the rotational effects of the blades on the helicopter. In doing so, we get a better story about the components, and we still get a good story about the lift. But our new story about the rotation becomes worse. The reason for this is that once we include the effects of the torque of the main rotor here, it would predict that not only does the helicopter lift, but the body spins around and around and around as it's lifting. So by including, say, by de-idealizing the mechanical components, we get more accuracy in that regard, but we get less accuracy. I should put a point up here, but less accuracy. So we've got lift, we've got components, but we have not good description of the rotation. Now, another thing we could do, of course, is that instead of adding that in, we could add in the rotational effects, the torque induced on the body by the tail rotor here. That would induce a similar sort of situation where we get more accuracy on the components, but we also get induced a rotation in the body of the helicopter, which is not accurate because when the helicopter is actually lifting up, the body doesn't rotate. It's only when we, as it were, de-idealize both components at once, the effect of the torque of the main rotor and the effects of the tail rotor, that the two rotational effects end up canceling out, and we get a version which is accurate with respect to all the dimensions that we've considered so far. So this is a really simple toy example, but it's meant to illustrate the idea that accuracy in general is going to be a partial order. There's not necessarily going to be a linear order on accuracy. And as one of the significant features of this, right, is that when we talk about representational accuracy, we will often have to try to specify in what degrees or types a particular model is more or less representationally accurate. And so this account draws attention to this feature, which is sometimes neglected. Good. I think I've already mentioned this example but maybe I'll say I think I've already mentioned this example, so I will go through it to talk about function. So the question of the function of idealization is the question of why use idealized models. Now, philosophers have recorded many different usages here. One is to facilitate computation or prediction or some other scientific activity. Another is pedagogical insight. Sometimes idealized models are used in those contexts. Sometimes idealized models are used in exploratory contexts. where one is trying to explore a new topic. And sometimes they enable explanation or to promote understanding. And distortion, I think, can aid in any of these activities. So one of the things that has been a trend in the literature has been to associate certain types of idealizations with particular functions. So for instance, a very well-known paper by Michael Weisberg associates idealization by distortion with this particular function here, facilitating computation of prediction, and associates it moreover with a kind of transience, that it's a type of activity which is temporary within science. On my account, there's no necessary connections between the forms of any particular idealizations and the functions. The forms and the functions can match up according to the contextual details of the scientific investigation. It may be that there are lots of cases of a particular type of idealization that perform a particular sort of function, but there's nothing intrinsic to the form of idealization which requires that it be towards one function or other. So this is sort of
ask another clarification question.
Sure. Let me just say that you might state this generally as a pluralistic attitude about the relationship of form and function regarding idealization.
So
go ahead.
It should be important then that any form of idealization can in principle play these functions.
Yes.
So that seems really possibly controversial, but also kind of significant. So there's no limit to an idealization of a particular form playing an explanatory function, for instance.
That's right. That is my position.
I agree, but I think that's really interesting.
Good. I mean, sometimes, when one is developing a philosophical position on a controversial topic, one hesitates because one thinks that one is saying just the obvious things. And so I'm very pleased to know that the things that I think are more or less obvious to the point of being uninteresting are in fact to others possibly controversial and very interesting. So I appreciate that, Kareem. Good. So there are many functions. There's a particular form for idealization, as I understand it, and many functions, but there's no necessary connection. Okay, so now let's go on to the justification question. So here's the orthodoxy. The orthodoxy says something like, using idealized models is justified when their distortions make little difference to the modeling task within. Oftentimes, modeling task is specified more specifically to particular predictions, say, but I'm being quite general here to keep in mind that I think that the function of idealization is variegated. So I surprised myself a little bit by more or less agreeing actually with the orthodoxy that this is generally the way that idealized models, the use of idealized models are justified. But I think we can be a bit more precise here. One is that we can say a little bit more by way of describing what make little difference means. Now, oftentimes it's tricky to define this because it's very tempting to define makes little difference by reference to some perfect model, that describes exactly the phenomena within the class of models that one is considering. But as I've just described to you, I want to demur from accepting that there will be in the class of models we're considering a perfect model. So we can't describe makes little difference in terms of relative closeness to a perfect model. So instead, my proposal is to understand makes little difference as being the fact that within the class considered, there is an upper set of the representational accuracy partial order, such that the differences between the model, the idealized model one is considering, and the elements in that upper set are within some bounds that one's considers acceptable. So maybe I can draw a little bit. So I'm imagining here, and this is quite simplified, but we imagine a partial order, right, of models where we have some sort of ordering in terms of representational accuracy, some structure that may look like this within a class. So it might be that the model that we're working with is this one here. Now, to say that there is an upper set of the representational accuracy ordering such that all of the elements within that upper set, it makes little difference. That using the idealization makes little difference means that there exists some element, say, for instance, this one, which is more representationally accurate. So it's above the model we're using in the representational accuracy ordering, such that it and all of the ones that are more representationally accurate than it in the class that one is considering. So in this case, that would be these here, that each of these, right, if one were to use them for the particular modeling task, that one would come to the same sorts of answers or conclusions, or if not the same, those that are sufficiently close. So one of the things that this makes, that this shows is that whether or not an idealization is justified is going to be relative to the, you might call them the values of the scientific community that's using them. Because the threshold about what little is not something that is going to be determined intrinsically by the theory itself, but it's going to have to be something that is introduced externally. That's not necessarily to say that it's merely a matter of opinion. It could be that that information is induced by external information about how accurately we can measure things and the scientific community's general agreement on that accuracy. That might be something that determines it. But those features, of course, are external to a theory of the phenomenon usually. I want to mention, though, that establishing this can be really difficult. It's highly non-trivial, except in really simple toy cases to do this. So in practice, scientists generally don't give a full justification for using idealized models. They give a kind of promissory note. In practice, they use inductive or empirical methods to try to suggest that we have evidence that an idealization is justified, rather than directly showing that an idealization is justified. We do that not by, for example, showing that all models in some upper set make little difference to the modeling task, but one, for example, selects a few of them and shows that it makes little difference to the modeling task. That's a kind of inductive method. Or an empirical method might be doing the same, but with simulations. And this is related to robustness analysis. Indeed, my understanding of one of the main features of robustness analysis is providing inductive evidence for the justification of an idealization for a particular modeling task. So what I mean to emphasize by this is that it's often the case that in particular circumstances, there is a substantial scientific activity involved in providing evidence that an idealization is justified. And in realistic cases, it's actually somewhat rare for us to be able to provide a full direct proof of a justification along these lines. Good. So let me give you an example of what I have in mind, coming back to the cosmology case again. So you might be worried, right? These FLRW spacetimes, they say everything's the same in every direction and everywhere. And of course, we look around and that's not what we see. And so you might get to worrying that what of the conclusions of these space-time models, do they crucially depend on these idealizations? In particular, right, if it were the case that we were to find a more representationally accurate model, would it change our conclusions about the general history of the universe? So physicists have done some work to try to provide these sorts of justifications. Let me just mention a couple interesting results along these lines. So there's a nice result by Ehlers, Garrett, and Sachs that show that if you can measure a uniform, then there's some other background assumptions here, but let's not get too technical. If one can measure a completely uniform cosmic microwave background, this entails that the structure of space-time has to be given by these by an FLRW spacetime. Now, we know, of course, that this assumption of a uniform cosmic microwave background is not exactly correct. It's only the case that the cosmic microwave background is almost uniform. So there's this other result by Stoger, Martins, and Ellis that show that an almost uniform CMB leads us to almost FLRW models. But of course, that theorem also has some other idealizations in it. And so the process continues to repeat, where scientists attempt to refine and provide evidence for for why a particular idealization is justified by theoretical and other sorts of investigations. So this is something that scientists are actually interested in. I would say contrary to some claims recently otherwise. So for example, Angela Potocznik has a really interesting book, Idealization in the Aims of Science, where she claims that scientists generally are not interested in this sort of activity. And I think in general, that's not correct. I think that scientists are interested in this sort of activity, and we can find concrete examples of it. Let me give a comparison now that I've given the form, function, and justification of idealization to this other notion that sometimes appears called idealization. Excuse me, called approximation. So maybe I can give a story here of how I understand the relationship. So you'll remember here that I had a picture where we have phenomena and we have models, and we have a representation relation. Now, usually the models themselves are not mere elements in a set, that the models themselves have structure. One of the ways that they maybe have structure is that they represent values of certain properties. So we have another map from models, say, into a space of values of a property. So this might be, for, this space here, it might be a line. If a real line, it might representing, saying, the value of some field or something like that. And we have similar sort of structure in the for the phenomena. And we can compare how the representation relation induces a relation between values here and values here with respect to particular models. Now, oftentimes what we can do then is we can then compare, if we're interested not just in comparing whole models of phenomena to the phenomena, but only looking at particular parts, we may only be interested in looking at how the values of a certain property approximate or similar to values of the property and phenomena. So approximation, according to my account, concerns one or a few properties of phenomena, and we replace, right, the space of models by a space of values of a property. Now, in a certain sense, this sort of notion of representation is entirely analogous, except that it's only partial. The models themselves, of course, may in the first place only be partial. So I see this difference here between idealization and approximation as not being such a strong difference. I would say the main difference is that a particular approximation where we select some values in this property space associated with the models that we're using to represent phenomena may not pick out any model in the class considered. So in a certain sense, if we're only interested in a particular fragment of what a model represents, we can use approximations to good effect without worrying about how those approximations, without worrying about how the corresponding values of the property link up with any model that represents in total, right, the phenomena that we're interested in. And the reasons why that might happen is it might be that the values of the property that we're interested in using to approximate the values of the phenomena may not find themselves altogether in a single model. So on my account, the relationship with approximation is pretty close. Approximation maybe just happens at a different level of analysis than idealizations. Okay. So there's a nice example of this that I'd like to illustrate, or that I like to use to illustrate. So this is considering Newtonian gravitation as a kind of essential force. So normally, when we understand the Newtonian gravitation postulates that the force between two bodies is proportional to the product of their masses and the inverse square of the distances between them. So we can imagine an object like the sun, right, and a planet like the Earth orbiting around it. And we might be interested in calculating this trajectory here, this orbit. Now, of course, Newton's theory describes that just as the sun exerts a gravitational force on the Earth does on the sun. But we may approximate, for example, the motion of the sun as being, well, approximating it as not as being motionless, even though, of course, the sun does receive a motion from the gravitational force of the Earth. And in doing so, we describe the trajectory of the Earth under a central inverse square force, rather than considering it as arising from a moving sun. Now, of course, that description with Newtonian gravitation as a central force is not a model of Newtonian gravitation, right? There are no situations that Newtonian gravitation describes where the two masses exert a finite force on each other, yet one of them does not move if gravitation is the only force being exerted. So that would be an example of an approximation in the context of Newtonian gravitation. It should be noted that whether a particular relationship is an approximative relationship that's not also an idealization is therefore relative to the class of models that one is considering. Having a more expansive class of models might allow one to, as it were, promote an approximation to an idealization. And having a more limited class of models might mean that there are many more approximations of interest that are not captured by any particular idealization. Okay. So I've talked a little bit now about the form function justification of idealization and how I see it relating to approximation. So now let me say about why we might go about using these. And I think it's for explanatory and other activities. So for this, I want to reference a debate that folks have had, especially in reference to examples like phase transitions, but also the Aharonov-Bohm effect and others within physics about the role of idealizations. This is a classification due to Eli Scheck. He describes two sorts of positions, essentialists and dispensabilists, and we can classify them in this sort of way. They see that idealizations are essential for activities like explanation, right? That without essentialists see that without idealizations, certain explanations of certain phenomena would be impossible. Dispensabilists, on the other hand, think that idealizations are merely pragmatic moves for certain sorts of explanations, that they are in principle removable. Essentialists see this essentiality as evidence for the importance of emergent phenomena, whereas dispensabilists see the pragmatic nature of idealizations as evidence or compatible with a general reductionism in science. So I would like to take a kind of ironic position and say that these are all right, actually. They're not as incompatible as they seem once we understand them in the right way. So to show why each of these is compatible, why we can have a bit of each of these. What I like to do is make a distinction between explanation and non-explanation. Well, so normally in this debate is couched in terms of whether or not idealizations are essential for some explanation or other, full stop. But I'd rather like to think about the role of idealizations as facilitating better or worse explanations for other sorts of scientific activities. And if that's so, right, it can allow for rules for both emergence and reduction in science. Okay, so I take it that the justification, my story about how idealizations are justified, indicates that idealizations are not essential to providing some explanations or other, but what they do is they often enable better explanations. Eleanor Knox has a nice paper where she argues that this is by facilitating abstraction. That is to say, by simplifying the models so that the explanations given involve reference to fewer properties or less complex properties. I think that's the case sometimes, although sometimes I think it's also by introducing new concepts. So I agree with Eleanor that idealizations often enable better explanations, but I think the way that they do that is only sometimes by facilitating abstraction. Sometimes it's through other means. But this basic idea is right, that the role of idealization is that they facilitate better explanations, or actually, for that matter, better versions of whatever sort of scientific activity we're interested in. That might be easier calculations for deriving predictions. If you think that explanation and understanding come apart, it might be that it facilitates better understanding, or it might facilitate better pedagogical roles, for instance, or it allows one to see further within a research program if one is undergoing exploratory research. And the way that it allows us to do this is that the idealized models have emergent properties. And all that I mean by emergent here is they have properties that are comparatively novel with respect to the other models in the class that we've been considering. So I'm taking comparative novelty here as a characteristic of emergence. I have some papers where I give like a more formal account of what this is supposed to be that takes advantage of the structure that I was referring to before. In particular, when I was describing how similarity relations on the phenomena induce similarity relations on the models, we can describe comparative novelty as comparative dissimilarity amongst the models. And so this is an important way in which that similarity structure allows us to give a precise definition of which properties of models, idealized models in particular, are emergent in this perhaps weak sense of being comparatively novel. And being comparatively novel, of course, just means relatively dissimilar. And as I understand it, this is the sort of story is compatible with reduction. When we understand reduction as an activity that involves, say, explaining the success of a certain class of models that we know to be idealized, say, or somehow deficient, in terms of some class that we think is more representationally accurate in various sorts of ways. That can involve explaining empirical success or other sorts of successes of those models. And I have a longer story to tell about that, but I'll have to save that for another time. So examples of how this works, coming back to the examples that I introduced before, in the case of cosmology, it's the extra symmetries that the idealizing assumptions of FLRW space-time induce that allow us to show or give an explanation that a very few properties actually determine much cosmological structure, much more than one might have been attempted to say ahead of time. So it facilitates a better explanation because it allows one to, as it were, get to describe the brunt of, or the large extent, at least at some coarse-grained level, structure of cosmological models by reference only to a few properties. In the example of phase transitions, I think that we should understand these cases as enabling novel explanations because they allow us to introduce new properties or new concepts, not because necessarily they facilitate abstraction. So the thermodynamic limit, which is a limit that where we hold the density of some thermodynamic system constant, roughly speaking, while we take its number of elements and its volume to infinity, allows us to give a definition of precise phase diagram boundaries. And it does so because it's only in this limit that the Helmholtz free energy can be non-smooth at particular points. And so we use those points of non-smoothness to define the boundaries between different phases. So there's this new property that arises, that is to say precise phase boundaries, right? That we are definable only once we take this limit. And that is the thing that facilitates simplified explanations and descriptions of phenomena. And in the case of population biology, the infinite population limit allows us to have in the model an emergent determinism in genotype transmission. It allows us to show how for sufficiently large populations, there is an almost determined frequency distribution for a particular genotype under these particular conditions. And that in turn allows us to explain under certain ecological conditions why, for example, features about drift in the short time limit, also where mutation doesn't matter, give us stable transmissions of particular genotypes. Okay, so those are some quick answers to those particular examples, and I'm happy to discuss them in more detail. At the end here, I just want to come back to some answers to the guiding questions. So remember, I started with this question, what exactly are we doing when we employ idealized models? And the story is roughly that we're using a model not as representationally accurate as some other that is available. So how can something so wrong, right, be so right? Why would you use something worse when you can use something better? Well, what we're doing is we're trading some representational accuracy for some other sort of scientific virtue, such as explanatory power or a scope of understanding or some sort of pedagogical value or so on. And that trade-off is an important part of the human activity of science. Sometimes increasing representational accuracy, which is one virtue of a particular model, means that the model loses out on other virtues. If our goal in a particular task is more attuned to those other virtues, then idealization is the right move. Now, even though I haven't talked about this so explicitly, you'll see that my story that I've been giving about idealizations doesn't make any distinctions between finite and infinite idealizations. And indeed, I think that there are no important substantive differences between infinite idealizations and finite idealizations. What's important in every case is that the idealization gives rise to some sort of emergent property that facilitates, for example, better explanations or deeper understanding or pedagogical strength or so on and so forth. Right. Thanks for your patience and your kind attention.
Thanks so much, Sam. That was really great. So as is standard for these sessions, we'll take a 5-minute break. Just to make things a bit cleaner, we'll start again at 5:40 rather than starting exactly on 5 minutes at 5:39. So we take student questions first. If anyone has a question, then just put Q in the chat and maybe put in brackets if you're a student. But yeah, we'll reconvene at 5:40. See you.
Oh, Sam left.
I think we should stop the recording as well.